Hi, this is Dr. Remenacker. In this particular video, we are going to start looking at a review of exponential functions and start the review of logarithmic functions. We're going to lead off with exponential functions. Exponential functions are functions, as illustrated in this first equation, where you have some type of a coefficient, a sub 0, this could be 3 or 6 or 2.7 or who knows what, times a number. A is going to represent some number here raised to an exponent. The exponent is where the variable is. That's why these are called exponential functions, is because the variable is in the exponent. When you have an exponential function, there are two criteria that need to be met for the base a. Those criteria are, first, that a must be greater than 0. Secondly, a cannot equal 1. If a were to equal 1, I mean, 1 to any power is still 1, so it really wouldn't do anything. Two examples of exponential functions are provided for you here. The first of these is going to be y is equal to 1.07 raised to the x power. In this case, the base is the 1.07. The exponent is x. And the graph of this function is going to look like what you see right here. To the left on the function, you'll see a situation where it's running asymptotic to the x-axis. And as you move to the right, it increases and increases at an increasing rate, which is something that's characteristic of an exponential function. That's exponential growth. Okay. This is the basic graph that you'll see anytime that your base is greater than 1. 1.07 is greater than 1, so you get a function that looks like this. It is typically the case that the y-intercept is going to have a value of 1 because at the y-intercept, remember the x value is 0, and any number raised to the 0 power is 1. The way that this can change from 1 to some other value is if your original function, looking back up at the first line of the notes here, in your original function, if a sub 0 is something other than 1, for example, it was 3, if the x value is 0, you're going to have your base raised to the 0 power, which is 1, times your coefficient 3, which would then give you something like 3. So that's how you could move the y-intercept away from y equal to 1. The second example of an exponential function that we have in this case is 1/4 raised to the x power. Here the base is between 0 and 1. Okay, remember when we initially defined a function that's exponential, we said that the base has to be greater than 0. Okay, 1/4 is greater than 0. However, the function's graphs will behave differently if the function is between 0 and 1 than if the function is greater than 1. So you see here to the far right on the screen a situation where the base is between 0 and 1. In these cases, as you move from left to right, the graph will be decreasing and will run asymptotic to the x-axis the further you move to the right. Let's take a look at a brief example here of a situation with a exponential function being used. Let's take a look at a first example here of a situation where an exponential is typically used, and it's something you'll be familiar with. This is the case where you have interest being compounded. Okay, so in this case, you're told that you are going to invest $10,000 at 4.1% interest annually. Now, this may be the APY, the annual percent yield, which is something that you should run into in one of your economics classes or something. But whatever rate at which they're compounding the interest, the annual percentage yield is 4.1%. The function that we're going to use is p of 0 times 1 plus r raised to the t. And this is the amount that you're going to have at any point in time. This is a function that you've probably seen elsewhere, and we will be using this throughout this course. So that's just one of those functions that's kind of assumed that you're familiar with and know. So what we're going to wind up doing here is we're going to have our initial investment, p sub 0 is $10,000. Remember, we have the 1 plus the rate raised to the t power as the second portion of the function. The 4.1% is converted back from a percentage to a decimal, and that value is substituted in for r, which is going to give us 1 plus the 0.041. Add those together and you get 1.041. Now, sometimes people ask, where does the 1 come from? The 1 ensures that you retain the initial $10,000, and the 0.041 is then how much you move beyond or in addition to the initial $10,000. Okay, so we have our function created. This function will allow us to then estimate, or actually compute, the total interest that will be earned over some period of time. If, for example, you invest this and you're going to let it ride for 8 years, the question is, how much will you have in 8 years' time? Well, you take your initial value of $10,000 times the rate at which it's going to grow. The 1 ensures that you retain your $10,000. The 0.041 is your interest rate. The 8 in the exponent is the number of years, and when you pop that into your calculator, what you wind up with is a final value of $13,791.32. On problems like these, I'm hoping that you won't ask me how many places do you want this rounded off to. When you're working with money, typically we round it to the nearest cent. Okay, so it'll be 2 digits to the right. Let's take a look at a second situation. In this case, it's not a growth problem, but a decay problem. You can run into situations in either direction. In this example, it says a small town starts out with a population of 36,000 people in the year 2010. In that same year, the primary employer in town moves the operation to another state. This type of thing happens when a company's offered a better tax rate or some kind of other incentive to move their operation from one city to another. This is a common thing to have happen. Once the company leaves, people gradually find jobs in other locations and move to other towns. By the year 2020, the population of this town has dropped to 29,500 people. In this case, you're asked to compute the average annual decrease in population. Without another business in town to provide employment for these people, they need to go elsewhere to seek employment, so the population of the town does decrease. All right, so to start this out, we're going to go ahead and identify that our equation that we're going to use is going to be 36,000 a to the t. The 36,000 comes from the initial population. Just like in the previous problem, the initial value was the $10,000 that was invested. Then we're going to have our a, which is going to be our base, raised to t, the number of years that are going to have passed. Okay, we have 2 pieces of information here. The first is that at time 0, the year 2010, the population is 36,000. We're given some additional information. 10 years later, the year 2020, the population has reduced or decreased to 29,500. We also know that A is defined as 1 plus or minus R. Since we are decreasing, because it's decreasing, we're going to be using minus. In the first problem we worked with the interest being compounded, the value was increasing, so we used the plus sign. Here we're going to use the minus sign. So we're going to have that the A value is equal to 1 minus whatever the rate of decay is. We can take this and we can rewrite this equation. Notice here I'm using the 36,000 from the initial population. 10 years later, I know the population is going to be 29,500, and 10 years later means the value of t is 10. I want to solve for a to the 10th power, so I'm going to divide both sides by this 36,000, which will give me a to the 10th is equal to 0.8194. To solve for a, what I want to do is apply the 10th root to each side. Now, computing the 10th root on your calculator is not that hard. Okay, so realize first that we're applying the 10th root to each side. And on the calculator, the way I'm going to compute this is 0.8194 raised to, you can either put this as the 1/10 or as the 0.1, whichever you want to do. Typically on something like this, I'll put in the decimal. This is how you would compute the 10th root of this particular value, which is going to give us an a value that rounds off to be basically 0.98. Okay, now we have two definitions for a at this point. One of these definitions is that a is equal to the 0.98, the number we just computed. The other definition we have for a is that a is going to be 1 minus whatever the rate of decay is. Taking these two different definitions for a, I can combine them, the 0.98 and the negative or the 1 minus r, okay, and I can solve for r. We can set these equal to one another because both of them are equal to a. There are two different ways to write a, so I set them equal to one another. Solving for r, we get that r is equal to 0.2. This tells us that on average, the population is decreasing at a rate of 2% a year. Now, this doesn't mean that every year the population goes down by exactly 2%. Some years it may be more, some years it may be less than 2%, but on average it works out to be a 2% decrease each year over that 10-year time frame that we're looking at. We'll continue working with exponential functions, but recall this is just a quick review to remind you, oh yeah, this is how exponential functions work. What we're going to do now is we're going to move on to a function that is an inverse of an exponential function, okay? Logarithms, okay? As is stated here, a logarithm is the inverse of an exponential function. Just like subtraction is the inverse of addition, division is the inverse of multiplication, logarithms are the inverse of exponential functions. What a log does is it returns a value that is an exponent. Okay? You'll see that in each of the three examples shown below. Okay? Remember these two things. First off, a log is the inverse of an exponential function. Secondly, a logarithm is always an exponent. To see how this works, let's take a look at the three examples provided here. If we take the log base 3 of 9, that's equal to 2. This is the same thing as saying our base of 3 raised to the second power gives us our value of 9. Notice here the 2 actually is the exponent. In the second example, we have the log base 4 of 64 equals 3. This is the same thing as saying 4 raised to the third power is 64. And if you check it, 4 cubed is 64. In our third example, we have the log base 5 of 625 equals 4, which can be read as 5 raised to the fourth power is 625. There are situations, and it's quite common, where you will get a negative value out as the exponent. For example, let's say we have the log base 3 of 1 over 27, this is going to be a negative 3. What this says is if I take 3 and I raise it to the negative third power, well, let's see, that's going to be the same thing as 1 over 3 cubed, which is going to be the same thing as 1 over 27, which is the resultant value indicated. Remember, with a log, you can get negative values out. You can get positive values out. The values most often will not be integer unless it's something that's been carefully designed to provide an integer result. Most values for logs are going to be some type of a decimal value, and the log value, the right-hand side, is always the exponent. As we continue working with logs, keep in mind that the value that is returned is an exponent. Okay. With this in mind, let's compute the value for x in each of the following cases. Okay, so the first thing I want to do here is I want to rewrite this log in terms of a base raised to a power equals a final result. In this case, we're going to have x raised to the third power equals 8. To solve for x, I'm going to apply the cube root to each side. So if I take the cube root of this and take the cube root of that, what that's going to give me then is x is equal to the cube root of 8, or x is 2. So for this particular problem, we could write this as the log base 2 of 8 is 3, and we can check that. This says 2 raised to the third power gives you 8, which is true. In the second case, we're going to start out with our base of 3 raised to our exponent, which we don't know right now, equals 1/3. The resultant value is always in the argument of the log. Okay, so what we have here is a situation where we wind up with the reciprocal. If you'll recall, 3 to the negative first power is equal to 1/3, which gives us then, we have an x value equal to -1, and we can rewrite this as the log base 3 of 1/3 is a -1. Why don't you pause the video here briefly and try this third one for yourself. It's the log base 2 of x equals 4. Hopefully you actually paused the video and worked this out for yourself. We have a base of 2, an exponent of 4 equals x, which is going to allow us to then compute 2 to the 4th is 16 is equal to x. From there, we can take and we can rewrite the function as the log base 2 of 16 equals 4, and that takes care of that for us. Okay, so for this video, that should be enough for you to think about. Remember, the objective here isn't to give a complete teaching of exponential functions and logarithms, but to provide a brief review and overview of those for you.